Okay, well, welcome back everyone. We have reached the beginning of Chapter 6. Primary topic of Chapter 6 is gases, and primarily what we're going to want to look at with gases are gas law-based calculations. So there are multiple mathematical equations called gas laws that will relate different physical properties of gases to each other. We'll get into the ideal gas law in a couple minutes or so. And what I want you to think about in particular, there are 9 or 11 gas laws, and it depends a little bit on which ones you identify as separate laws and which ones you kind of lump together. But I think if you kind of focus in on how to approach solving problems here, if you learn one of them, the ideal gas law, you can use that as a basis to derive any of the other gas laws. So there's not a lot of benefit to memorizing which one is Boyle's law, which one is Charles' law, etc. Because even if you memorize them, you still have to figure out which one is appropriate for the problem you're looking at. So keep that in mind as we go through some of the sample problems. I'm going to try to show you how you can start with the ideal gas law and use it to get to the right equation for a problem that uses one of the other gas laws. Okay, so to start looking at gases, there is one new set of units we need to think about, and those are the units that will describe the pressure exerted by a gas on its surroundings. So the primary unit that we will use for pressure is called the atmosphere, and this is going to be abbreviated as ATM. For atmosphere. Now be careful, I've seen people confuse that with atoms, and it's not the same as atoms. I'm not even measuring the same thing as atoms, so just be careful about that. But we'll use that primarily as ATM. Now, an atmosphere is defined as the standard pressure of the Earth's atmosphere at sea level. So it's pretty reasonable for studying gases because it's about the pressure of the Earth's atmosphere around us at any given time. However, atmospheres are usually not the way pressure is directly measured. So if you measure pressure with a barometer, in the US, we usually use inches of mercury. So originally a barometer was a column of mercury, and the pressure of the air would push that mercury up an evacuated glass tube, and you just measure how high the column of mercury was. So if you ever see the pressure on, say, a US weather report or a weather website, it'll be inches of mercury. In terms of the metric system, though, we usually will measure pressure in terms of millimeters of mercury. So another common unit for pressure is the millimeter of mercury. And what will often happen is we're given the pressure in terms of millimeters of mercury because that is how we'll read the barometer, but we'll see there are cases where we'll need to change to atmospheres to make sure it matches with other units that'll be incorporated in a problem. Now, millimeters mercury actually has another name that is sometimes used, which is torr. So one of the original developers of the barometer was a guy named Torricelli. So there's a unit of pressure that is sort of named after him. It's actually not a capital T, and I don't know exactly why that's the case, since it does come from his name for the unit. So sometimes you'll see pressure written in torr, sometimes you'll see it in millimeters of mercury. They're exactly the same, so they are completely interchangeable. I kind of think millimeters of mercury is a better unit because it gives you that physical description of what is happening. But the primary thing you'll want to be able to do is convert from millimeters of mercury or torr to atmospheres. So it is helpful to know that 1 atmosphere is equal to 760 millimeters of mercury or torr. So if we're given one measurement of pressure, we'll switch over to the other one when it's appropriate. That again is something we'll see when we get into those problems. Now, once we have pressure, we can think about the ideal gas law. And the ideal gas law, this is the one I'm going to use to kind of at least start every problem. So sometimes it'll get us to another equation, sometimes we'll just directly use it. So the ideal gas law is PV equals nRT. pretty easy to remember, and it even rhymes. If you repeat it to yourself, I think 3 times, you will remember it forever. Right? Just be careful not to do it in front of the mirror at midnight. You might invoke the ghost of John Dalton or some other famous scientist. So make sure it's daylight when you do that. In this equation, P, you may imagine, is the pressure. And what we're usually going to want is to have the pressure in atmospheres. Now, I'm going to explain why that is as we go through all the pieces here in this equation. V is the volume of the gas we're looking at, and we're generally going to measure volume in liters if we're using this equation. And then moving over to the right side, N here stands for number of moles. So this would be how many moles of gas are in the gas sample we're looking at. T here is a capital T, is the temperature. And temperature here is in kelvins. So when we're talking about gases, we always need the temperature to be in Kelvin. Now, the Kelvin temperature scale is just offset from the Celsius temperature scale. So if you're given a Celsius temperature, you can add 273 to it to get the Kelvin temperature. So Kelvin is degrees C plus 273. And generally 273 is fine. The actual number is 273.15, and you can go quite a bit further than that in terms of the actual lowest temperature in the either temperature scale that would correspond to 0 Kelvin would be minus 273.15 or so degrees Celsius. The other symbol here is R. That's not actually a variable. R is the gas constant. So it always has the same value, right? So we really won't do any problem to where we're solving for R, right? We'll just use R. And R is the reason why I put specific units with each of these things. The value, or at least the most common value to use for R, is 0.0821. And the units associated with that value are liters times atmospheres over kelvins times moles. So when we use this equation, the ideal gas law, and we use this value of R, what we need to do is make sure the other units match the units that are present in R, because to get to the answer we're trying to solve for, we'll need to cancel out all of the other units. So here's why we may have to change from millimeters of mercury to atmospheres. And if you're given some other measure of volume, you might want to change that to liters. And if you're given the mass of the gas and you know its formula, you could change that to how many moles of gas, etc. Temperature is almost always going to be measured in degrees Celsius, so you can convert that to the Kelvin temperature before you plug in to your gas law. And this is something to be careful of, particularly since we just talked about thermochemistry in the last chapter. When we're talking about thermochemistry, we're dealing with changes in temperature, in which case Celsius and Kelvin are interchangeable because they are the same degree size. A 10-degree temperature change is a 10 Kelvin temperature change. But 10 degrees Celsius is not the same as 10 Kelvin. Right? 10 degrees Celsius is actually 283 Kelvin. So when you're doing a gas problem, always change to Kelvin. When you're doing a thermodynamics problem, you can always leave it in Celsius for your temperature change. So you could still change it to Kelvin, you'd just be adding a lot of work to your problem. Okay, so I've got a couple examples here, right? And not just this page, there's a few more examples. This is pretty much a problem-based chapter. So I'm going to stop the first video there. We'll pick up with the next couple chapters in the next video. And again, I want you to focus on how you think about approaching the problems, because there are lots of gas laws and it can be intimidating to try to memorize all of them, but you don't need to. You just need to learn how to apply them. We'll do that in the next video.